Hi everyone. In this video, we're going to introduce a general solution to defeat all forms of return-oriented programming. But first, let's briefly review how we can exploit memory corruption vulnerabilities to perform an attack. We have encountered many memory corruption attack methods in this class, such as format string and buffer overflow. In such attacks, we change the control flow of the program and return to the memory address where we have injected our malicious code. They are defended by marking certain memory sections, such as stack and heap, as non-executable. Then we have return to libc and ROP that don't rely on injecting codes into memory. In ROP, we chain gadgets together to make the program execute functionality as we intend. There have been many defense techniques that prevent ROP. For example, we've seen ASLR in our class. But ASLR can be circumvented by brute forcing on a 32-bit machine or by de-randomizing addresses of certain functions. Here, we're going to present an approach that was described in the paper G-Free. Essentially, it is a compiler-based defense that builds gadget-free executables. The executables do not contain exploitable instruction sequences that terminate with a free branch. In this way, we can defend any return-oriented programming. In the paper, the author describes 8 different techniques of changing different kinds of exploitable codes to harmless code. We will just talk about the 3 most interesting ones in this presentation. They are alignment sleds, return address protection, and immediate and displacement reconstructions. There are 2 things that we want to keep in mind while we talk about the techniques. First, let's take a closer look at gadgets. In each gadget, there are 2 parts: code section and linking section. Linking section should end with a free branch instruction that changes the control flow of the application. It could be a jump or return instruction. This is a general form of ROP attack. Second, in ROP gadgets, except for codes that explicitly have return or jump at the end, there are also unintended free branch opcodes. They are codes that do not return or call in their original intention, but accidentally contain like 0xC2, C3, CA, or CB in their instruction that can be interpreted as a return. The first technique that we want to introduce today is alignment sled. An alignment sled is a sufficiently long sequence of opcodes that don't affect the execution of the program, such as a knob sled. An alignment sled will be set to the maximum length of knobs to tail an instruction. Therefore, regardless of the alignment prior to reaching the sled, the execution will eventually land on the knob sled. This is used to prevent attackers from using unaligned codes, because no matter where they start to execute the code, after the knob sled, they are forced to realign with the actual code. In the following example, the code's original intention is to move something to EDX and then rotate. However, if the attacker manages to execute the code from 04, the remaining bytes are equivalent to the instruction add something to AL and then return. This is exploitable. To protect, we could inject knobs before D0C3 so that these 2 bytes will always be interpreted together as rotate, no matter where we start to execute the code. In another word, C3 will no longer be interpreted individually as a return. You may think that this approach is somewhat inefficient because we need to execute knobs, but this inefficiency could be easily avoided by a jump at the beginning of the alignment sled, so that if we execute the program from beginning, the sled will be skipped. Another interesting technique is called return address protection. It is a protection that prevents an attacker from executing code that contains a return from an arbitrary position of the code. Specifically, at the entry of a function, we insert a header that encrypts the saved return address on the stack, and then we add a footer to decrypt the return address before return. The encryption could be a simple exclusive OR of the return address, with a random number as our key. In this way, without knowing the value of the random key, If an attacker jumps into a function at an arbitrary position and uses the return instruction, he will provide a return address. When the code reaches our footer, the attacker's return address will be decrypted to an invalid address. The program will then return to that invalid address, and the attacker will no longer have control of our program.
Okay, let's now look at the third technique, immediate and displacement reconstructions. This is a technique that replaces certain arithmetic, logic, and comparison operations with other instructions that give the same result. The reason we want to do this is that since these operations can take an actual value as operands, they could contain free branch instruction opcodes, such as OXC2 or OXC3. Let's look at this example. By itself, add OXC2 EAX simply adds 194 to whatever is contained in the register EAX. However, this code is vulnerable to ROP because it contains an explicit OXC2, and OXC2, despite by itself, could be interpreted as a return. So how should we fix this? To avoid an explicit OXC2, we could instead alter the instruction to add OXC1 first, and then increase EAX by 1. Okay, let's look at the second example. What goes wrong here? Well, similarly, OXCA by itself could also be interpreted as return, so we also want to avoid an explicit OXCA in our code. So how should we fix this? Well, we could use the same strategy. We can first add OXC9 to a register, increase that register by 1, and then do our XOR operation. Okay, now let's look at a demo that illustrates the technique that I just explained. Let's look at this C program. This program has a vulnerable function to ROP because it contains this line of code. X equals X plus 194. As I mentioned before, 194 in hexadecimal is OXC2, and we don't want an explicit OXC2 in our machine code because it could be interpreted as return by itself. To show you more clearly, let's first compile the code to assembly code and then to machine code. Let's take a look at the assembly code. As you can see, the vulnerability occurs here. Add 194 to this address. We are going to fix it by first add 193 to this address, and then increase the address value by 1. Let's now take a look at the machine code. As you can see, here is the explicit OXC2 byte that is exploitable. Since we did not find an official G-free implementation online, and other implementations on GitHub were not compatible with our environment, so we implemented our own version of G-free following the paper's guide. And by the way, the original C program's output is just 194. G-free is a compiler-based tool that does not require users to change their source code. So we wrote a Python script that pre-processes the assembly code. As we can see, it first reads in the original assembly code, then it searches for instructions contains 194, and then it replaces the 194 by 193, and then increase the original destination's value by 1. This is a simplified implementation because we made an assumption that whenever 193 appears in our assembly code, we are adding the number to some register. Now let's run this script. And you can see we get a new assembly code, test gfree.s. And if we compile based on this new generated assembly code, we get a new program, test gfree. Let's take a look at its output. It is still 194, so the program's functionality has not changed. Let's now take a look at the program's machine code. As you can see, the original OXC2 here is now replaced by OXC1. So this function is no longer has that original vulnerability. This is the end of our presentation. Thank you.